Okay, so it's my great honor and great pleasure to come back to Bonn and to give this talk. So I would like to thank the organizers, especially Daniel, for putting together this wonderful workshop. I will also want to thank Daniel because scientifically we benefit a lot from the interaction with him. So, okay, so I'm going to talk about this solving multiscale PDEs, and I'm going to talk about numerical homogenization and also the fine scale solvers, basically. Yeah. So this is a joint work with Hummel Hardy. And here is the model problem. So because we have already seen a lot in this workshop, so basically we just solved this main benchmark problem. And if you use numerical homogenization, or if you use any multiscale methods to solve the elliptic equation, the basic assumption is you want to solve the right-hand side multiple times. And so it would be the multiscale method would be good to solve the time-dependent problem or eigenvalue problem, for example. Okay, so there are a lot of methods to solve those problems, and there are two types. One is the fine-scale solvers, and the most important method is probably the multi-level method. So multigrid, subspace correction, AMG, and there's also other types of method, hierarchical matrix, and also multi-resolution analysis, because if you have so that's very natural if you have a wavelet decomposition, and that's very natural you have multi-resolutions, and you can think about to use that to do coarse graining or homogenization. Okay, and people has already tried that, but that does not work very well, so I will say. And so, and for multiscale solvers, so there is a HM method, and that to solve the effective equation and multiscale finite element if you want to get oscillations, and also VMM. Okay, so in this talk, we will talk about this. Okay, all right. So that's our definition for numerical homogenization. So you have already seen this before. So we have scales 1 and scale epsilon, which is the smallest scale of your problem. So basically, you want to put a mesoscopic scale, computational scale, capital H, and that's determined by the computational power or maybe the resolution you want, the accuracy you want. Okay, and usually this capital H is associated with degree of freedom, so that's coarse degree of freedom. So with this scaling, and the goal is to construct some good space. Okay, good space in the sense you can have the quantitative error estimate, for example, something like this. Okay, and this constant usually we want this independent of oscillation. Okay, of course it would be best if it's also independent of contrast, but in this talk I will just talk about variation. Okay, oscillation, and with optimal alpha. Okay, so there's different choices for this norm. So I think Daniel recently prefers to use L2 norm, but in our case we use H1 norm or maybe the energy norm. Okay, and this space is constructed by pre-computed subproblems. Okay, so hopefully this is localized, and also for basically you can do this in parallel, and this is independent of the boundary conditions of the right-hand side. Okay. So before I'm going to the method, so I will say something about the low dimensionality of the solution space. Okay, suppose you have the L2 right-hand side, so you have the low dimensionality of the solution space. So we found this in 2 dimensions by using these harmonic coordinates. So this harmonic coordinates is solving by this equation. With x is x1, x2, so that's basically, so if d equal to 2, that's 2 values. Okay, you can show that this f is actually homomorphism when d equal to 2, but unfortunately this does not hold for d equal to 3. So there are some counterexamples. Okay, so there are some counterexamples. This does not hold, so it's not mapping. And if this is true, if this is really a mapping, and you can show that this U itself is just you can the best you can hope is h1 plus some epsilon, depends on the media. But when you look at the u in the f coordinate, it's much more smooth, and it gives you h2 regularity. So basically, you can approximate u in this space without the h accuracy. Okay? So, but this only holds in 2 dimension. Okay? So, and afterwards we say that, so actually this solution space, if the right-hand side belongs to L2, and we can have the homomorphism between the solution space and the H2 space. That's very easy, right? So you can have the same right-hand side, but you solve the divergence A gradient, and also you can solve the Laplace. Okay, you have a one-to-one mapping. So basically, this solution space is a very thin subspace of H1. And if you just approximate H2 functions in H1, you can get all the H accuracy. Okay, so how can you do this for the solution space for divergence A gradient? Okay, so actually you have such kind of results. Okay, if you have an n-dimensional subspace, so let's say this is Vn of H minus 1, that's somehow strange space, but you can show such approximation results. So this approximation for the solution with A, okay, this approximation error with the solution space with respect to A is actually, this error is controlled by the approximation error for Laplace. Okay. But the bad thing is, if you do this, usually you get a non-local. You don't get a localized basis. You get a non-local basis. Okay. And this actually, it can be shown that this is chromologable of n ways. And in H1 norm, it's actually n to the minus 1 over d or capital H. And if you do something like this, okay? In the previous paper, it's done by the so-called flux norm, but now you can just, it's simplified like this. Okay? So basically, we can say that this solution space is actually low dimensionally, and we have the optimal error, but the thing is, how can we find a good basis? It's a localized basis. Okay? So there are many ways to do that, for example, LOD. And I will show you something which is different. Okay? But actually it's very close to LOD. You will see that. So that is called Bayesian framework. Okay? So let's say what is the Bayesian numerical analysis. So this is a paper by Don Connis, and many years ago, 30 years ago, and he proposed such an example. So suppose we have a function, okay? So some function, okay, any function. Suppose we know the values of f at some points, like x1 to xn, and how to approximate f. Okay, so that's the numerical analysis 101, right? Okay, so you have 1,000 methods to approximate that. But this Diaconis is a statistician, so he proposed this Bayesian approach. So we can just put a prior on the continuous functions. Okay? And because we already know the values of f at these points, so we can calculate the conditional expectation, okay, of f given the prior and given these known values. Okay? So I just gave you some example. If this prior is a Brownian motion, okay? If this prior is a Brownian motion, and so what is this expectation? This expectation is just piecewise linear interpolation. Okay, why is that? So that is because, so if you have, that's 1D case, and you have these points, x1, x2 to xn, okay, and you know the value of f, okay, you know the value of f at these points, okay, and you want to compute this conditional expectation. Okay, so because this is Brownian motion, so it's independent. So we can just consider the case if this x is in xi between xi plus 1. Okay, so this is just because it's Brownian motion, so this just equal to xi fi plus 1. Okay, so this conditional expectation is just this. Okay, and for Brownian motion, so basically you hold your f value at these 2 points, and in between this is Brownian motion, and you can calculate this conditional expectation is just the linear interpolation of these two. Okay, so basically this is just these two sum up, and which gives you fxi phi ix. Phi x is linear basis plus fi plus 1 phi I plus 1 x. Okay, so so this gives you this conditional expectation, and at the same time it gives you the basis, right? Okay, so this conditional expectation in general is just sum fxi phi I x, right? Okay, so if the prior is the first integral of Brownian motion, and it gives you cubic splines, and you can do further, so that it gives you a splines of higher order. So all this means, so this approximation basis can be obtained by putting priors and do conditional expectation. Okay, and this is optimal in some sense, right? This is optimal in the MSE sense and corresponding to the prior. What happens if you have two variables? Let's say that. Okay, let's say that. Okay, so this is just for function approximation, right? So what happens if we have a PDE? We have an equation, or if we have two variables, right? Okay, so we can propose the following question. So suppose we have a PDE, and we want to find what would be the, and we know some observables of the solution. Okay, for example, the average of U at some volumes of the edges, or maybe, okay, and somewhere. Okay, suppose we know we know these observables of U at some, so we have this psi I, and this psi I is measurement function. Okay, so and we know that this is the solution U of the minus divergence A gradient U equal to F. Okay, what is the best guess of U? Okay, so that's the question. Okay, so we have this Bayesian formulation which proposed by O'Hady a couple of years ago, and so analogous to the Bayesian formulation for the function approximation. So what we're going to do is we first do the randomization of the problem. Okay, so we put a prior on U. What would be prior? What would be a good prior? So we just put something at the right-hand side. Okay, so this could say is a Gaussian field. For example, it can be white noise, or it can be some noise with Gaussian field with covariance function correlated. Okay. Okay, so because this is linear, okay, so well, if this is linear, so because C is a Gaussian field, so this U is also a Gaussian field, and we can calculate the covariance function. This G is a Green's function of the elliptic operator. Okay, and because we know this observable, so the good approximation basis can be obtained by conditioning. Okay, so we just calculate the posterior this expectation of U given psi, and similarly we can get something like this, and this is observables, and this is corresponding basis. Okay, and what is phi I? So you have to calculate this phi I, but it's not a very hard calculation, but you can get that. Okay, so it's something like this. Okay, this theta ij is just covariance matrix of psi, these observables. Okay. Okay. Yeah, with respect to the prior. Yeah. We will have to put a prior first, right? Okay. Yeah. Okay. So now we have this basis. Okay, and we have the formula for the basis. And okay. So we have this Bayesian framework for the numerical homogenization, and basically we can get this optimal approximation basis by conditioning. Okay, but so we need to have some concrete examples, because we can choose different lambda, and we can choose different measurement functions psi. Okay, so that's the freedom to choose. Okay. So you can choose lambda equal to dart function, and that would be the white noise. Okay, and now this gamma is just the convolution of the Green's functions. Okay, so actually, so if I write down this L is minus divergence A gradient, this elliptic operator, and this gamma is actually the fundamental solution of L square. Okay, so this gamma is the fundamental solution. L square gamma equal to delta function. Okay, okay. Yeah. Well, and so basically from this formula, because this gamma is the fundamental solution of L square, and this phi I just belongs to the span of this guy. Okay, you put the right hand side your measurement function, and you solve for the L2 u equal to psi I. So. Okay, so this phi I, this basis just belongs to this span. Okay, so if the covariance operator is L itself, well, this is somehow, it's a little bit difficult to understand, and that's defined here. Okay, okay. So if the covariance operator is L itself, the gamma is just Green's function itself. Okay, and this phi I, because you put gamma here, this phi I is just belong to the span of the solutions with psi j at the right hand side. Okay, so it's the same space. Okay, and so we have also we have different choices for the measurement function. Okay, so if we choose the measurement function is a dart function, and you have the point value, you have the point measurement. Okay, and if together with this lambda equal to dart x minus y. So if we choose the random field to be the white noise, and we actually recover this so-called rough polyharmonics plans, which we proposed a few years ago. Okay, and you can also choose psi I. So this has a better physical meaning, and that's characteristic functions of edges or volumes. So that's you have the edge average, you have the volume integral, something like that. Okay, okay. And that's a connection with LOD. Okay, so if you have a coarse interpolation operator, you have the Clement or something else, and you can actually find the corresponding psi with this coarse interpolation operator. If you have a Clement operator, that would just be the patch average for the nodal patches. Okay, and that actually recovers LOD approach. Okay, so. Well, here we have this formula, but in practice we cannot calculate this formula. We need to find a good way to calculate this basis, right? Okay, we need to find a good way to calculate this basis. So what we do? So we need a variational formulation for this basis. Okay, and so suppose this L is an elliptic operator, and you can define the solution space. Okay, the solution space is something like this. You have the right-hand side belongs to L2, and you can also define the scalar product. Okay, it depends on which covariance functions you choose. You have different scalar product, and also you can define. So because we choose this Vi is a space such that the measurement for index I is 1, and the measurement on all the others are 0. Okay, so we just choose this as our basis. The constraints. So we can have this following variational formulation, and this phi I, the basis which you see from the previous slide, is just minimizer of this guy. It's a constraint minimization problem. That's at this point it's actually almost the same as LOD. It's just you can choose different measurement function right? Okay. So that's the variational formulation. Okay. And you can have the two-scale decomposition, and you can have the optimality, which you have seen. And so this two-scale decomposition is something like you have the call space, and the call space is the span of this basis. And also we have the fine space. The fine space is the space such that all the observations are zero, observables are zero. Okay. And we can define the corresponding norms, and we have this optimal recovery. So basically that means the call space and the fine space, they are orthogonal. Okay. So you have the optimal recovery of U in V capital H. And also you have the optimal approximation property of this U of capital H. So basically this U in is the interpolation of U in the call space. And you have this approximation error. This is controlled by order H. Okay, the right-hand side is L2 just. And this is true for the following constructions. So if we have the RPS basis, so RPS basis is a little bit more difficult to analyze because this is corresponding to a fourth order equation. So it belongs to this space. Okay, it's a linear combination of the fundamental solution of fourth order equations. So this is but we can do that but we can have this such kind of with so-called higher order Planckian inequality. Okay, so once we have this, and we can have this approximation property, and if you have the volume or edge average, you can just use usual Planckian inequality. And if you have LOD equals interpolation, and you have already seen that. Okay, good. Once we have that, and we can say that, and you have seen this many times in this workshop, so you will have the accuracy of finite element solution. So because we have the accuracy of the interpolation, and this is conformal, so we have the accuracy of finite element solution. And we have this exponential decay of the global basis. Okay, so for the previous constructions. And we have the truncation error for the localized basis. So basically, we can have the accuracy of finite element with localized basis. And so that's localized to a region of h log 1 over h. Okay, and in that region, and you can say that the finite element accuracy is order h, and given that the right-hand side is L2. Okay. Okay, so there are some numerical examples. So this is just this RPS. Okay. And so this coefficient is just some random media. There's some realization of the random media. And if you choose the linear finite element, so you have a long pre-asymptotics. And this rough polyharmonic splines is defined like this. So it will minimize this divergence A gradient norm, the R2 norm of this guy, and subject to this constraint. Okay. So why we do that? Actually, at the beginning, we don't realize this Bayesian framework. And the starting point is we want to minimize this Dirichlet energy. But this is not a well-posed problem. I think Daniel also knows that at that time, right? So, but what they are doing is they turn to the coarse interpolation operator. And what we are doing is we use this higher order derivative as a regularization to do that. Okay? And actually this way, and to use the higher order derivatives to do this regularization already exists for the computational geometry. In this computational geometry community, they already do something, and they call this polyharmonic splines. Okay, and because we have a rough, so we call this rough polyharmonic splines. Okay, and suppose we have the domain and we have these scattered points, and we can add constraint that phi xi is 1 and phi xj equal to 0. So that's we just have this constraint, and we have the basis, and basis, well, you see that it has a sharp decay. And if you look at it in the log scale, so you can clearly say that there is a exponential decay from the center. Okay, but unfortunately, this is globally supported, and we can use the exponential decay property. Okay, so if we put this RPS basis in the original elliptic equation, we can get this the the convergence rate we want. Okay, so that for the H1 is n to the minus half, and for the R2 is n to the minus 1. Okay. But this is global, so we have to do localization, and you also have seen this before. So this is coarse mesh with mesh size capital H, and we refine this fine mesh, and we have some mesh size H, which less than the smallest scale epsilon. And we can have patches, so patches with layer 1, with layer 2, layer 3. Okay, so we can localize the computation of the RPS basis from global to local domain. Okay, and so we can have this formulation of this localized RPS. Okay, so we want to find this phi I. Okay, it's defined on these local patches with k layers. Okay, it also satisfies this following constraint. And that's the decay of the single basis. Okay, this is decay of the single basis with respect to the number of layers. Okay, the R2, H1, so it decays exponentially. And here it's so for the each line here, it means you have the number of layers equal to 1, 2, 3, 4 until 7. Okay. Okay. So if you look at the fixed degree of freedom, and what you can see is actually, if you, for example, that's if you look at the fixed degree of freedom, that means you increase number of layers. Okay, and so when k equal to 1 is here and k equal to 2, 3. Okay, so if you that means if you further increase layers, it does not get you a better result. Okay, so that's the saturation basically. Okay, if you have a fixed degree of freedom, you can only get order H accuracy. Okay, and okay, so that's H1 error and that's R2 error. Okay. Okay. So that's basically if you have the R2 right-hand side and you can get this this error is controlled by order H. But what if you don't have the good right-hand side, and or what if you have something you have to look at the fine scale solution? Okay. So if we really want the fine scale solution, so one way we can do that is we can get a very fine grid, and we suppose we have a nested grid. Okay. So suppose we have a nested grid, and this we call this tau k, and the mesh size hk is just h to some power k. Okay, h for example 1/2. Okay, and so for this 2D example, we can build the index tree. So that's a code tree index, and for 1D you have a binary tree index. So 3D you have outcome. Okay, so you have an index tree. So that's ik, and so we can solve the basis at each level, of course. Yeah. So we can solve the basis at each level, and we denote it by phi k, and with the measurement function psi k. Okay. And we know that this phi k is a minimizer of the following constraint minimization problem. Okay. So basically, this the observation. So we will have the measurement. The measurement is delta ij, and we minimize this norm. Okay. And we know that this span of phi k is just the span of L inverse psi k. For example, if we just choose this norm to be the A norm, okay? If we just choose this norm to be the A norm, so this span is this span. So usually, so we want a nested basis on the nested grid, okay? So because we have that, so basically that means if we have a nested measurement function, then we have a nested basis, okay? So for example, we just choose this psi k to be the characteristic functions on the elements, okay, on the case level elements. And this measurement function would be nested, okay? And because of this, this is a linear relation, so this phi k, this basis, is also a nested basis, okay? So that's something more technical. So we have these linear relations of this. We have the pi would be the interpolation operator of for these measurement functions. Okay. So and we have so correspondingly we call this Vk is the span of the basis. Okay, this Vk is the span of the basis, and because the measurement function has this linear relation, so we also have this basis has a linear relation. So we have this because we have this nested property. So we have this restriction matrix. Okay, so we can extract this interpolation matrix, a restriction matrix, interpolation matrix, and also we can calculate the stiffness matrix, right? Okay, that's all we need for example, for designing a multigrid method, right? For example, okay. But we can do something further. Okay, so what do we do? So let this Wk, okay, this Wk be the orthogonal complement. So this A orthogonal complement of Vk plus 1. So this basis at k plus 1. Sorry, this should be k minus 1. Okay, this should be k minus 1. Sorry. This is on the coarse basis. This Wk is orthogonal complement of the basis on the coarse level in the basis at kth level. Okay, with respect to the A naught, for example, this scalar product, and we can have the index set of this Wk. Okay, so now we can have this construction. So from the basis at kth level, okay, so we have this linear mapping. So with this linear mapping, we call this W, this matrix W, and this maps from the basis at kth level to this W, this orthogonal complement of this Vk minus 1 of the coarse basis in the final basis. So we have this linear relation. Okay, this forms the basis of Wk. Okay, so basically, as algorithm, what we need to choose? We need to choose this pi. Okay, this pi is as local as possible. This pi is interpolation from the k plus 1 level to kth level. We want this to be as local as possible, and we also have freedom to choose W. Okay, so this W, so we choose that such that this holds basically means it satisfies constraint. Okay, it satisfies this measurement should be equal to 0 constraint. Okay, and we also want this W transpose equal to identity, and that's something we have. This W has a very good condition number. Also, it does not enter into the calculation. Okay, and it's also as local as possible. Okay, good. So we have the algorithm to calculate this transformation. Of course, we don't want to calculate the basis at each level. Okay, we don't want to calculate the basis at each level. That would be too costly. Okay, so we actually calculate this transformation. So at the finest level, we just use, for example, the usual linear basis. Okay, that's qth level, and from the qth level to 2 levels, so we just do this from the bottom level to the topper and topper level. And this W, which defines this W, which you preset, okay, which gives you this chi. This chi is Gamblet. It's in the orthogonal complement space, okay. And once we have this chi, and we find what would be the basis on the k minus 1 level, okay. So, and this is solved by the orthogonality. So basically, you have this Bk. This Bk is a stiffness matrix on the for the Gamblet on the kth level, and so it involves this calculation. So that's the main solve. Okay, and now you construct the interpolation matrix. That's because this interpolation is because the basis at k minus 1 level is just a linear combination of from the Gamblet space, from the A orthogonal space, and the space at k. Okay, so you have this. And this is actually the most cost part. This most costly part is here. Okay, so all this is not so costly, but the most costly part is to assemble the stiffness matrix at k minus 1. It's not so costly. Well, at this For the exact, it's costly, but for the localized, it's not. Okay? So that's localized. Okay? So previously, I just told you, so that's exact because all the bases are globally spotted. So if you really calculate that, there you get nothing. Okay? But if you want to get something, you have to use exponential decay and localization. And the only place you do that is here. Okay? So you just to solve this guy. Okay, that's the only place you use this localization. And there is a rho k minus 1. That means this rho k minus 1 is you can choose a fixed value. That means for each level, and you choose your basis at the support of radius rho times hk. Okay, so you just at each level you do that. At each level you do that. Okay, so using this property, it can be shown that this this construction of this basis and also the linear solve and can be achieved by this n log n to the power 3d. Okay, and that's actually comparable to the H matrix method. That's 2d plus 8, and for d equal to 2, so this is a little bit smaller, but it's log, so yeah, it's not. And also for the hierarchical interpolative factorization of Lexan-Yin and others. Okay, so it's actually okay. So I will just show you some pictures, and we have this Gamblet decomposition. So we have this W space. It is a orthogonal complement. Okay, so we have this whole orthogonal decomposition here. Okay, and you can actually project your solutions in these spaces. And what you get is this UQ equal to, plus, for example, is this U1 and plus U2 minus U1 plus U3 minus U2. So that's what you get. Okay, and UK is the solution, is a Gaussian solution in Vk. Okay, in the exponential basis at level k. And so if you have the right-hand side, which is pretty smooth, so what you get is something like this. So that's level 1, level 2, level 3, and for all these levels, they have a very small energy. Okay, and if you have this right-hand side is, for example, a delta function, and you have many energies in the final levels, and that gives you a sense of what is high frequency, what is low frequency. Okay, in terms of energy. Okay, so so basically, if you want to have less than 1% accuracy, you need to go to the finite level. Okay, and what is the property of this exponential decaying basis? So first is exponential decaying, okay. And the second, we have this lemma. Okay, we have the R2 and H1 estimate, okay. So we have H1 estimate, and which you have seen before, and we have also, it's not hard to prove the R2 estimate. Okay, and you also have the inverse inequality. That's actually very useful. So you have this A norm is controlled by the R2 norm and controlled by CHK inverse, and even you can prove this because this guy divergence A gradient, it belongs to R2. Okay, so its divergence A gradient way belongs to the summation of the measurement function, and if you choose some good measurement function, so it's R2. So you have this higher order inverse inequality as well. Okay, so you have this inverse inequality. And what would be the property of Gamblet decomposition? So for these Gamblet subspaces, so it's true that all these spaces, they have a bounded condition number. Okay, the condition number is controlled by this guy. Okay, so although this, because we say that hk equal to h to the power k, and h is just 1/2, so all these are bounded, uniformly bounded, and this say it only depends on the A, but not depends on the oscillation. Okay. So we also have the bounds for AK for the stiffness matrix. So for the stiffness matrix, we have something like this. Okay. So we can control this spectral norm of AK, and this lambda k is just controlled like this. Okay. Good. So we have all these good properties of Gamblet decomposition, and what I have just shown you is this all these are proved for the global exact gamblets, but you can also do this for localized, but it's more technical. And numerically, you can actually show that this is also true. Yeah. Not only numerically, but you can also show that it's true. So if we do localization and we have the sparsity, and that's what we use for efficient calculation, and we also have the condition number are uniformly bounded. So we show that the condition number of stiffness matrix for each subspace. Okay, so that's from 1 to 7. So that's that's 10, that's 100. Okay, so that's something this maybe it's bounded here. And the condition number of the overall stiffness matrix, fine scale stiffness matrix, is something like this. Okay, so basically we can distribute this stiffness over the subspace. Okay. So once I just show you that we can calculate the stiffness matrix, we can calculate the restriction operator, we can calculate the prolongation operator, and now we can just design this gamblet-based multigrid, right? Okay. So that's a very simple version. So actually, that's somehow I took it from Susan Brenner's book. So that's a very simple version of that. And so there's no pre-smoothing, and there's only error correction and post-smoothing. Okay. And so at the k equal to 1 level, we just do the exact solution, and for k greater than 1 version, we do the error correction first. Okay, that's basically that you project your error from the k-1 space to the k space. And then you do post-smoothing, and we just choose the simplest, which would be the Richardson iteration. Okay, this lambda k is a spectral norm of AK. Okay, and the output of the case level iteration, we call that it's MDKZ not G. Okay. Okay, so we want to prove this convergence of gamblet-based multigrid. And actually, because of all these good properties of gamblet subspace, it's actually very easy. Okay, and so we have these arguments from Hackbush, from Brenner, and we have the approximation property and the smoothing property. So that's what we want to prove. And the approximation property is something like this, which we already have. And we want to prove the smoothing property, and that's something like this. Okay, and you have the Obinish argument, and you have the L2 estimate. So basically, from this L2 estimate, and you can get the H1 error. Okay. So from here, and it's not very hard to get that the reduction factor is controlled by this. That's typical multigrid results, but here we don't have the regularity. Basically, the usual ones you need the regularity, or people use this kind of mesh-dependent norms to prove that. Right. Okay. And so that's somehow the old convergence proof of the multigrid. There's new convergence proof of the multigrid. And also, actually, we're inspired by Professor Ralph Hober's work. And so that's actually, so we want to check whether or not this satisfies this subspace correction framework. So actually, it satisfies very well. So we can prove that the stability of the decomposition. So now this space decomposition is not the same as Professor Rauchhofer's construction, because his construction is additive and our construction is multiplicative. Okay, and but still this framework applies to both cases. And we have to prove the stability of the decomposition, so it's something like this. Okay, and because of this WK, they are orthogonal, so you can actually just do this level by level. Okay, and you have the Cauchy-Schwarz type inequality. That's also because of the orthogonality of these subspaces, and that reduces at each level. You just justify this. Okay, so then because of all these good properties of the Gamblet subspace for this estimate for lambda k and inverse inequality, and you can show that this is actually true. Okay, these are true, and all these constants do not depend on the variations of the coefficients. It only depends on, well, contrast. That's unfortunately, so we have this guy. Okay, so that's some numerical results. And so that's the multigrid with a bilinear basis, and that means the geometric multigrid. And this is with layer 1. So layer 1 is not good, okay? So layer 2 is here. Layer 3, 4, 5, 6, and also the exact gamblet are here, okay? And that's for this high contrast. Actually, that's from SP10 example. And so this is a residue, this is error norm, and this is random checkerboard. So for this guy, it's actually even better. So you can see that after 1, 2, 3, 4 iterations, it converges. Okay. Okay. So I think I will. So that's my time set up. Okay. So I will finish my talk here, and thanks a lot.